It's great to be here. Thank you, everyone, for coming to my talk. And a big thanks to the organizers for inviting me to be here. It's been great so far, and I'm very grateful to them for being flexible enough to postpone my talk, which was meant to be this morning. I don't often get the opportunity to teach. I'm a research scientist here at IBM, so I've been looking forward to this summer school and having the opportunity to teach at the summer school and do a crash course in quantum error correction, which is hopefully less crash and more course, as the joke goes. My own work, so today's talk, as you know, is going to be about quantum error correction. And quantum error correction shows up in many different areas of quantum information theory, in communication, thinking about sensing. But my own focus and the focus of today's talk is going to be on computation. Before I get started, I just wanted to say, please feel free to interrupt at any time. I want to ensure that I cover material thoroughly, and whatever I do communicate is done clearly. So if you have any questions, please interrupt. I've also got, by the way, my pen with me. I think I should be able to point to things and write. Excellent. So if anything's unclear, I can also just write on my iPad. OK, so enough preamble. Let's get started. I'm going to start with probably the most important result in the theory of fault tolerance. It's called the threshold theorem. It's one of the crown jewels of the theory of fault tolerance. And it basically guarantees that quantum computation is possible. That sounds like hyperbole, but hopefully I'm going to convince you that it's true. And we're going to use that as a sort of guiding light for the rest of the talk today. So to motivate the threshold theorem, we are going to start by thinking about a quantum circuit C that we might want to implement. The circuit C runs a quantum algorithm. And in generality, it's what the circuit C does is takes as input some quantum state psi, performs a series of operations. Each gate in the circuit is constructed using 1 and 2 qubit gates drawn from some finite gate set. And in the most general setting, this circuit can output some quantum state and some classical bit strings that come from measurements. Unfortunately, the output of this circuit, the computation that you want to perform, is unlikely to be reliable directly because the input qubits themselves that are part of this quantum state psi might carry errors, and the gates in the circuit themselves might be faulty. So just to give you an idea for the sorts of numbers that we're talking about, suppose, for example, you're in a setting where 1 in 1,000 gates fails, which is not too far from some of the numbers that we're seeing in different labs. Then roughly, you're going to be able to construct a circuit of size 1,000 before you're guaranteed to see one fault. And these faults can be catastrophic. They create an avalanche effect and ruin your entire computation. So that's not good. So you might be asking, if I were to limit myself to circuits of size at most 1,000, what can I do? And unfortunately, the answer seems to be not much, because many of the applications that we're interested in from quantum dynamics, finding the ground states of quantum systems, and Shor's algorithm itself, they seem to require very low failure rates, as low as 1 in about 10 to the 17. As time goes on, we expect the physical failure rates in our labs to decrease. We expect them to get better. And we expect, with theoretical advances, to perhaps not need as high of a demand on the circuits that we want to implement. Maybe we can make do with lower logical failure rates. But it's unlikely that these are ever going to meet in the middle. And it now becomes a question of how to bridge this gap. And the way that we do so is by using quantum error correction. And that's where the threshold theorem comes in. It says it's possible to simulate C using the noisy components that you do have access to. And there's a few ingredients that go into this threshold theorem. The first is a quantum error correcting code. And this is some way for you to encode your quantum state. It takes this k-qubit state that you begin with and creates a larger state, an n-qubit state, that now has some buffer room. And we'll see the consequences of that shortly. Let me just finish explaining what the ingredients of this threshold theorem are. The second piece of the puzzle is this fault-tolerant circuit, C. And what it does is to take, for every elementary gate that forms your circuit, C, that you want to perform, there's a corresponding gate. So these thick blue lines here indicate that it's the corresponding fault-tolerant counterpart. And these gates are trying to perform on psi hat, this quantum error correcting code, psi encoded in a quantum error correcting code. They're going to do the same as this gate would have done directly on psi. And the final piece of the puzzle is to interleave rounds of error correction between these fault-tolerant gates. And you need this because your input state, as we know, could itself carry errors, and the elements of your circuit could be faulty. So what you're trying to do is prevent errors from building up, and there's only so much of a buffer that your quantum error correcting code can provide, and you want to maintain the state within that buffer. Right? So if you were to take a sledgehammer to your quantum computer and smash it, and of course there's no error correcting code that can protect you from that. There's some limited amount of error that you're going to be robust against. So the whole mantra behind fault tolerance is to be able to correct errors faster than they appear. And the threshold theorem gets its name because you can show that using a quantum error correcting code, there exists this magic number called the threshold. And if each of your physical gates, if each of the gates that form the circuit and also the input qubits, if they fail at a rate below the threshold, then it turns out that you can perform error correction and correct errors faster than they appear. And doing so, you can achieve an arbitrarily low logical failure rate p hat. So p hat here is the failure rate of your fault-tolerant circuit c hat. It represents the fraction of the time that your circuit c hat differs from the ideal output c. The magic of the statement of the threshold theorem is that this p hat can be made as low as you'd like. So it's really a remarkable statement. At this point, you're going to stop and ask yourself whether it's worth it, whether it's worth constructing a quantum error correcting code and this fault-tolerant circuit, because although Shor's algorithm or other algorithms might promise what we believe are exponential speedups, the cost of constructing this circuit might be so much that it sort of balances out. So you go through all of this effort to construct this fault-tolerant circuit, but you put so much resources into it that you might have just stuck to a classical implementation. And the way that you measure this cost without sticking to a particular physical implementation, sort of agnostic to which implementation you pick, whether it's superconducting qubits, neutral atoms, or ion traps, sort of abstracting away the actual physical system and asking for these abstract costs are using what's called the width and the depth of these circuits. So what is the width? The width is the total number of qubits that your circuit is using. And this includes any ancilla qubits that you might use as scratch space, so all your qubits. And the depth of the circuit is the total time that it takes to run. And this includes any time that you might use for error correction as well. So you're accounting for all the time, you're accounting for all the space. And sometimes I might refer to the volume of the circuit, and that simply equals the product of the width and the depth. And is it worth it? If it wasn't, we wouldn't be here. So you might have guessed that the answer is yes. And how do we formalize this? We say that that there's a nice relationship between the depth of the fault-tolerant circuit and the input depth, and the width of the fault-tolerant circuit and the input width. In other words, they differ from each other by a product of what we say is a polylog factor in the volume of the circuit and the the logical failure rate that you want to achieve. Okay? If that sounds like mumbo jumbo, the point is that you're only paying a sort of log penalty. If you start with W qubits that you want to run, then you only need to pay W times log many qubits to run its fault-tolerant version. So you're not paying too much, but you're getting potentially exponential benefits in running these circuits. Yes?
So the threshold seems like it depends on like the circuit and the depth.
Yeah.
At least for like shorter depth circuits.
Yeah.
Do you ever get to a regime like a sufficient depth where the threshold becomes like circuit independent?
No, it's always going to depend on the details of your implementation. So the question for those that didn't hear it was how the threshold might depend on the details of the implementation. And it does. It depends on a lot of these details. And I'm going to get to that in a second. So you're assuming that there's a sort of uniform family of similar-looking circuits that you're trying to run, and they're all constructed using the same process. So that similarity then allows you to say a threshold is associated with a particular family. And I'll get to that in a second. Yeah, great question. Anyone else? Yeah?
Is there an optimal, like a proven optimal scaling for this overhead? Or?
We'll get to that, yeah. Also a great question. So the question was, if there's an optimal scaling for the overhead, why are we seeing these log factors? Could we do better, right? All this is saying is something is achievable, but we don't know if we can do better. And we're going to see that in certain instances, we may well be able to do better. Yeah?
So what's the assumption the threshold theorem guarantees that we can make p hat as small as possible? And as a real computer satisfy those assumptions?
We're going to get to that. We're going to cover all of that over the course of the talk. Yeah. All right, great. OK, so just to reiterate what we just said, if the failure rate of each of your components that go into your circuit is p, some small constant, and it's sufficiently small, then it's possible for you to achieve a logical failure rate, p hat, that's arbitrarily small with a penalty d hat and with a cost d hat and w hat for the width and depth of your fault-tolerant circuit. As people have just asked with these questions, this sort of statement is sort of unsatisfactory because these big O statements are only promising asymptotic scaling. They're only saying that as things grow larger and larger, good things are going to happen. But how large is large? How small is small? For example, if this threshold that the threshold theorem guarantees will exist, if it's also 1 in 10 to the 17, then it feels sort of hopeless because that's what we're trying to do to construct good circuits anyway, and this threshold is far too low for us to be able to ever achieve in practice, so it doesn't make any sense. What exactly are the error models that we're talking about? What does it mean for a gate to fail with failure rate p? What does that entail? Are they failing independently? What if you have correlated errors? What if you have bursts of solar radiation that take out entire patches of your circuit at once? They're not IID. They're like highly correlated errors. And it still feels sort of abstract. How are qubits laid out in space? I haven't told you anything about geometry. Maybe you're working with a system where qubits that are far apart can't talk to each other very well. But maybe the sorts of assumptions that are baked into some incarnations of the threshold theorem don't take that into account. So there's a lot of things that we haven't discussed, and we're going to iron out some of these problems. But that doesn't make this exercise of studying the threshold theorem and using it going forward doesn't make it entirely useless. So when we contrast some of these asymptotic guarantees, which is what they are, they're asymptotic in nature versus the real world, what you really need are people to then take these sorts of guiding principles and understand thoroughly what architecture-specific constraints are, whether some types of errors happen more than others. You need to understand and supplement these sorts of asymptotic results with detailed numerical simulations of your system at hand and tailor your code to the specific architecture that you're dealing with and try to make it as efficient as possible and hope that when you make things as efficient as possible by tailoring the code to your system, that this quantity, the p threshold, is large enough that it actually makes sense to run a quantum computer. Okay, so far so good. The reason that, yeah.
Sorry, I might be jumping ahead a bit, but is it just a matter of designing your code specific to the error model, or is it that you also have to make these assumptions when you design the gadgets? That, I mean, from my understanding, the assumption is that the noise model is normally taken to be Markovian when you find out this threshold. And I'm sure there are other sort of understandings of when it's not Markovian, but then it's not just a matter of designing code. You also have to go through all of this detail of finding how the gadgets work and all, go through decoding all the information.
Right, right. So it's all of it. That's right. So the question was, it's not merely a question of tailoring the code. There's a lot of aspects of designing a fault-tolerant circuit in addition to merely just picking an error-correcting code, and you're right, and we will talk about all of these things. Okay. The reason that the threshold theorem is still important and forms the foundation of our research effort is because without it, the search space is much too large. You have no idea where to look. You don't know what to do. In fact, in the early days of quantum computation, I was told that some believed that quantum computation was not going to be possible because it might be similar to analog computation, where when you're dealing with continuous things, you really can't perform error correction. So although this sort of in principle advantage exists, you can't actually do anything with this idea of quantum computation. It's merely going to be an idea. But with this with the prospect of error correction, then we're like, okay, this is no longer pie in the sky. We can actually do something with this. And this then guides you to search for good error correcting codes. This then guides you to search for more efficient types of fault tolerance constructions. Okay, so with that, we're going to dive into the meat of it, and we're going to break down the different ingredients of this threshold theorem further. The first part of my talk is going to focus on just the encoding map and not performing any computation on the information that's in an error correcting code. So we're just taking a state psi, and we are going to make it robust using this idea of a quantum error correcting code. And this then defines for you merely a quantum memory, no computation involved. Okay. The other thing that I wanted to add before proceeding is that there's different ways of visualizing this threshold. So what I've given you is a sort of guarantee asymptotically that such and such happens if your thresholds are small enough. One other way to visualize what's happening is that typically you're considering a uniform family of protocols, and they're all constructed using the same sort of recipe. These thresholds, as you pointed out, they're going to be functions of the way that you construct your circuit, the precise error models that you're dealing with. They're going to take all of these factors into account. When you look at papers, the sorts of pictures that you're going to see is that for a family of protocols, this threshold is important because as you increase the size of your circuit, you might get better at correcting errors. There's a sort of wholesale effect that's going on. The more you buy, the better you get. And that happens when you're below this threshold quantity. Okay, so that's another way of understanding or some more important features of this threshold that we often see. And as your circuit gets larger and larger below this threshold point, so these colors just indicate that the corresponding circuits are larger than others. As your circuit gets larger, you're going to see, hopefully, exponential improvement for a fixed failure rate. Okay? So this sort of graphical approach to understanding the threshold is useful because then it allows you to say some more things. It allows you to explore the space of what you might want to aim for in your lab. So suppose you have some target logical failure rate that you have to try and implement a circuit that you're interested in, Shor's algorithm, for example, and you know that as long as you're below this target logical failure rate, you're good enough. So then you might say, okay, either I can improve my physical system and reduce the physical failure rate in my lab until I hit this point, or I can try and achieve this using a much larger code. So I can try and construct a significantly larger error correcting code. And whether or not you want to make this trade-off is then up to you. Okay? So when you see sorts of threshold pictures in practice that come from numerical simulations, you're going to see these sorts of cartoons. And these cartoons then allow you to understand how to navigate the space of what to aim for in your lab. Do I want to reduce my physical error rate? Do I want to make my system itself larger? And you can go one way or the other to try and reduce the failure rate. So this is an example of how your logical failure rate might depend on the system that you're dealing with and the particular circuits. Right, so yeah, the very last point that I wanted to make is something that I've already said, which is that you might be happy with some sufficiently small failure rate for your logical circuit. Okay, so with that, diving into part one of the talk, which is introducing quantum error correction and purely from the purposes of thinking about quantum memories. Okay, so what are we talking about? A quantum error correcting code is some map from this Hilbert space, or the complex Euclidean space associated with k qubits, to the space of n qubits. And as protagonists of this story, we're just going to introduce some distinct states, psi and phi, and ask what happens to them under this error correcting map and also under errors. So as I said, this quantum error correcting code is an embedding into a much larger space. And Q itself is going to be some small portion of it. So corresponding to your states psi and phi, you're going to have some, when you consider distinct states to begin with, you're going to have some output distinct states, psi hat and phi hat, that correspond to them. When you have an error, and in this cartoon I've represented an error simply by rotating the symbol for the state 90 degrees, the hope is that it maps onto an entirely orthogonal space. And that way you can distinguish when you're in your code space and when you're not by asking which of these distinct orthogonal spaces is my state in. If they're not orthogonal, then you can no longer distinguish them and you might have created an error. Okay? So we might want to perform this embedding so that we can create as many orthogonal spaces as possible, because we might then say, for every possible error that I am likely to deal with, there's a distinct orthogonal space so that I can catch as many errors as occur. The other thing that I might want to do when we return to talking about logical operations and performing computation, this idea of a logical operation is one that could map one distinct state to another. Oh, sorry, a state to a distinct state. So you start with phi, and what do I have to do to map psi to phi? With these dashed lines here, I have the corresponding operation that maps psi to phi on the encoded space. Now, for performing computation, you might think that you'd like this to be as easy as possible. You want to be able to get from psi to phi easily. But the problem with that is that if you can do it easily, then nature can as well. And with very few errors, you might introduce an error when you didn't mean to. So in fact, you want to make it as difficult as possible, or sufficiently difficult to map from one state to another so that it doesn't happen accidentally. Okay, so this dashed line here might correspond to a fairly long path inside your Hilbert space. You might first have to perform some long map to some phi hat, and then map back to phi. And this long path guarantees that it's not going to happen by accident. And the distance of your error correcting code is sort of, again in this cartoon, the minimum number of operations that you need to perform to map from one code state to a distinct code state. Introducing some notation that I'm going to be using going forward to represent the most important parameters of the story. So far, this is going to be called an NKD code within these double brackets. And the name of the game in error correction is, I have some number of qubits k that I want to simulate. How do I minimize the total number of physical qubits that I need to pay for this while simultaneously making it as robust as possible? How do I increase the distance so that it's robust to as many errors as I can possibly make it? And what does error correction entail? So here's what you might do. You might say, okay, given this state, this incorrect state psi hat that's on its side, I can look at the state, see it's on its side, and then undo the operation. And I can distinguish it because it's an orthogonal state. And our ability to do so quickly and effectively is going to create for us a decoding algorithm, and this is something we return to. But again, high-level cartoon picture, this is what is happening. This, of course, is not going to work directly because you can't infer the state. And potentially, you might have, for example, a superposition of psi hat and phi hat, they're distinct states. And so if you were to ask the question, is my state in psi hat, you might wreck the superposition. So instead, what you'd want to do is merely ask a much more coarse-grained question, which is, what orthogonal space do I sit in? Which of these orthogonal spaces am I in? And this sort of coarse-grained measurement motivates the idea of what's called a stabilizer code. So these are our main codes, our go-to codes, and they have a lot of beautiful structure. By the way, these codes are going to be constructed using polymatrices. These are things that I assume that some or most here might be familiar with. If not, some of the properties that I'm going to be using are on the board here. The polymatrices, I'm going to be referring to X and Z, the two polymatrices that I've indicated here. The polygroup is the group that's generated by the imaginary number I times the identity X and Z, and P sub n is the n-fold tensor product of this. So hopefully people have seen this before. And some of the properties that we're going to be using, I've indicated here as facts. One, for every poly operator, you're only going to ever have plus or minus 1 eigenvalues. And that's going to be important. And the second fact that I'm going to use is this thing on board number 2, which is that if you consider any two poly operators P and Q, then they're always going to either commute or anti-commute. There's no other way. Okay? And these are going to be important properties. The poly matrices have some very nice properties, and these two in particular are going to help us design error correcting codes. Again, let me pause to see if there are any questions, because I said a lot without actually writing anything or including any more material. OK. Any questions on stuff that I've said in previous slides? Also welcome. OK, great. So what is a stabilizer code? A stabilizer code here is an abelian subgroup of the stabilizer group is an abelian subgroup of your space of n-qubit polys. So S1 through Sk are polymatrices that live in the space of n-qubit polys, and they all commute with each other, and this group is not going to contain minus identity. And the way that we define our quantum code is by choosing the common plus 1 eigenspace of all of these operators to be the code space. So since they're a set of commuting operators, they can be diagonalized simultaneously. They have a shared eigenspace. And this shared plus 1 eigenspace of all of these operators is going to form the code space. So this defines for you a stabilizer code. These states, psi hat and phi hat, are again going to appear in the story, and we're going to see what happens to them under the process of error correction. Right? Like, how do you actually do error correction? The way you do this is by projecting onto different eigenspaces of these stabilizer generators. So how do you do error correction? You do so using what's called a syndrome extraction circuit. And I explain what a syndrome is and exactly what this circuit is doing. The syndrome extraction circuit is really a projection onto the eigenspaces of your operators S1 through Sn minus k. If you were to input to this circuit psi hat and all of these n-silo qubits, there's n minus k of them. Okay? So these guys there's n minus k of them. Each one corresponding to one of your stabilizer generators. Then if your state is indeed in the code space, then it's going to pass through the circuit unaffected. What you're doing is asking the state the question, are you really here? And if you are, I'm going to leave you unaffected. On the other hand, using this fact that I've written here and also reiterated here, suppose your state psi has been affected by a poly error. So it's been mapped to E times psi. E is an error. Then one of two things can happen. When you perform your measurement, right, the measurement outcome that you get is going to be given by this inner product. And that inner product is either going to be plus 1 or minus 1, right? So polymatrices only have plus or minus 1 eigenvalues, and the way that we're going to get the outcomes of this measurement are determined by whether or not the error commutes or anti-commutes with the stabilizer generator. And those are the only two things that can happen. Okay? So if you have E times psi, if I were to tell you that the error that you're looking for certainly anti-commutes with the ith generator, then the ith qubit is then going to throw up a flag, and using that you can say, okay, I'm no longer in my code space, I need to do something. And you can say, okay, the ith qubit is 1, and now I need to undo the error. So that error has a representation. I can't directly observe the state, but I can extract this sort of classical information about the state. And I can use this extracted classical information that doesn't affect even superpositions of states in my code space. And using that classical information, I can do error correction. Okay? So this is what it means to do error correction. And this set of bits, 1 through n minus k, this is going to be a string of 0 and values. 0 if your stabilizer generator commutes with the error, 1 if it doesn't. And this string is called the syndrome. Right? So that's why the circuit is called a syndrome extraction circuit. It's the workhorse of constructing quantum memories, and later we'll see for constructing fault-tolerant quantum circuits. So this is the core ingredient. And yes, so as I said, the ith syndrome bit of the string sigma corresponds to the eigenvalue of your generator. And this is something that I want to reiterate. If you were to consider some other state, phi hat, rather than psi hat in your state, you're going to get the same string. So the string that you get only depends on the error. It does not depend on the state. And that way, if you have superpositions of code states, they're going to come out the same. All you can learn is sort of which of these big boxes that it's in, but you can't learn any more fine-grained information. Okay? So that was worth repeating, and motivates why, or one reason why we like to think about stabilizer codes. Okay, so what are these other spaces? What you're going to see is that using the stabilizer formalism, you can divvy up your Hilbert space associated with n qubits, this complex Euclidean space, into these orthogonal partitions. And each partition, I'm going to call them Q sigma, each of them is going to correspond to some syndrome. So they correspond to some different eigenvalues of your generators. For each string sigma, you're going to have a corresponding space. So this is a Q sigma for sigma. So this is trivially sort of a sigma equals all 0. And this is for some other string, and this is for some other string, sigma prime. So your entire space is going to now be partitioned based on the possible syndromes that you can see. And what's a logical operator? A logical operator, as we said, it's one that maps you from one code state to a distinct code state. Equivalently, it's an undetectable error. It's something that you don't want happening. And these are the set of operators that commute with all of your generators. If they commute with all of your generators, then you can't see them using the syndrome extraction circuit. And so this error is going to go undetected. Okay, so far so good? All right, so this is a sort of key ingredient in constructing quantum error correcting codes, and hopefully things are clear so far. Any questions? Yeah.
Something a little earlier in your talk, you talked about minimizing D given K and trying to maximize N, but are there architectures where minimizing D isn't necessarily the best metric? So maybe like I have a higher poly weight, but if it's all the same polys, some symmetric string, that's easier for me to correct than one that's lower weight, but all different polys.
That's a great question, and I'm going to talk about it on the very next slide. Yeah. So the question was whether or not, so this distance measure that I've just introduced is a sort of worst case metric. What's the minimum number of operations that you need to do to map from one code state to another? But if errors are just happening randomly, it's not like someone's out to get you. It's just random stuff is happening, and these random errors might not all line up in a way to create a logical error. So you might be asking, how does the distance affect my performance against this worst case metric? Tell me about the average case performance. It still sort of does, and we'll see how in a sec. Okay, great. I want to use this opportunity to introduce both the first error correcting code that we're going to see today, as well as sort of a graphical representation for quantum error correction, for quantum error correcting codes that turns out to be quite useful. in very many situations. So this is going to be a sort of classical code in disguise. It's really a simple type of code, but it's useful for introducing some notation. So what we're going to do is encode a single qubit in 3 qubits, and the associated stabilizers, right? So I need to tell you, to define a code, I need to define the stabilizer generators. And in this graph, the black dots represent my qubits, and each of these gray blobs, they represent the stabilizers. So anytime a qubit is connected by gray blobs, it means that the corresponding stabilizer is going to be x times x on those 2 qubits. And so since there's 2 gray blobs, there's 2 different stabilizer generators. And given this set of stabilizers, I can also tell you what the +1 eigenspaces are. That defines my code space. So it defines for me a mapping. If you give me 0, I'm going to map to Q of 0, and this is going to be the uniform superposition of +++ and -=-. 1 is also going to be a superposition of +++ and -=-, except there's going to be a sign difference between it. Equivalently, you can think of this in the computational basis as a superposition of states with either even weight, so the sum of all even weight strings, or odd weight strings. All right, as is indicated here, you can also think of this as encoding plus or minus. You don't have to stick to the computational basis, and this might even look cleaner. What happens if a single qubit Z error occurs? Suppose the very first qubit is hit by a Z error, so that corresponding state is now indicated in red. A Z error has occurred on the very first qubit. What's our rule? Our rule is that the stabilizers either, poly operators either commute or anti-commute. This XX stabilizer anti-commutes with a Z. It only meets it at one point, and so you're going to know something's wrong. That measurement is going to tell you that there's an error, and you're going to try and undo this. So you're going to raise a flag for that corresponding stabilizer. And this is a simple example of a decoding algorithm. Also, where does it fail? It fails when you have a logical operator, for example. If you have 3 of your qubits failing, then you're not going to see anything, and you're just going to suffer one state mapping to another. Okay? So this is an example of or an instance of what was just asked. This code is asymmetric, where if you have a single X-type error, you're going to map one computational basis state to another. But if you need 3 Z errors to map one computational basis state to another. So you're not treating all errors on the same footing, and this might be useful if in your lab some types of errors are more likely than others. You can maybe bias your code, or what we said earlier about tailoring your code to the specific types of noise you see. This is an example of that. You're saying, I only really deal with Z errors. I don't care about the X type. I'm just going to try and minimize resources for that. Okay, so far so good. Any questions? Great. Right, so also just a simple example of when your decoding algorithm fails. It fails when you're almost at a logical error. So if you had this ZZ error on qubits 2 and 3, then it's still going to be the case that it's just the first stabilizer that raises a flag. So both of these situations are going to look identical, and you are then going to correct onto the wrong state. So even though nature has not induced a logical error, it's pushed you far enough to the point where then you finish the operation and create confusion. And what if we wanted a higher Z distance? This is where the idea of a family of error correcting codes comes in. They all have similar properties. You can increase the size of this graph by including more stabilizers. So for every pair, you have X acting on that qubit and its neighbor. And the corresponding logical operator then is just going to be the size of your chain, and so you're going to be even more robust to Z-type errors. This also motivates arguably the most important error correcting code. It's called the Tor code. And this code is also endowed with a graphical representation and actually a lot more properties that are going to be extremely useful in studying quantum error correction. In the story, the qubits sit on the edges of this square lattice. So on every edge, there exists a qubit, and the stabilizer generators are associated with, again, geometric things. They're associated with the vertices of this lattice and the faces of this lattice. So for every vertex, I've indicated one of them here. So this plus sign indicates the stabilizer. The corresponding stabilizer is going to be x on the edges that are incident to that vertex. Similarly, this face here that I've indicated using a red square is also a stabilizer, and that's going to be z. That's going to perform z on all of the qubits that are adjacent to that face. And what are my logical operators? Here's one set. It's this ladder operator of x, x, x that runs from top to bottom. And then there's a z that goes sideways. So I probably don't have enough time to get into it, but you can prove for yourself that 1, all of these stabilizers commute, and 2, the logicals commute with the stabilizers. And if you toy around with it a little bit, you'll see that the distance of this code is going to be 3. The weight of this operator is 3, and you can't find anything shorter. To make our picture simple, it really is a pictorial. It lends itself to pictures, this code. And so we're going to take advantage of that. And to represent a stabilizer, or really a poly operator, I'm just going to use loops. So this blue loop represents a stabilizer. This other blue loop represents another stabilizer. And the loop runs over all of the qubits on which the stabilizer has support. I could also consider products of stabilizers, and they're just going to be longer loops. Likewise, I could replace my x-type logical with a blue string, my z-type logical with another blue string. And now I have completely pictorial representation using strings and loops of my error correcting code. Why this code is nice is because it's very closely associated with topology. This sort of lattice that you get, this square lattice where I've identified the rightmost side, these dashed lines, sorry, I should have started with this. These dashed lines indicate that the right side wraps over and touches the left again. The bottom dashed line indicates that it wraps over and comes to the top. And this forms a torus. And in this representation, what you've done is that you've taken your torus and drawn a grid on your torus. And the stabilizers themselves correspond to contractible loops on your torus. And the logical operators now have a very special form. These are the non-contractible loops in your torus, meaning you can't shrink them and make them vanish because there's the hole of the donut sitting in between. Okay? And the x and z type logical operator that I've just indicated both correspond to non-contractible loops. This qubit has 2 logical qubits, one x going this way, one x going around that hole. And similarly, 2 z-type operators, one going this way, one going that way. I've only indicated one of them here for simplicity. And this code, what are its parameters? It uses 18 physical qubits. It encodes 2 logical qubits, and it has distance 3. It's the shortest logical operator here has weight 3. And this code is great because it now has a lot of physical properties that we can rely on, right? Like there are variations of this code that you can embed on a tabletop, right? Because of this square grid feature, you can put it down on a tabletop, and every qubit has very simple connectivity. You just talk north, east, west, south. When I said, when introducing the threshold theorem, that there are some things that it leaves unsaid, it doesn't tell you how to actually take this abstract error correcting code and put it down in real space. Whereas this is now our first example of an error correcting code, and we understand how to plop it down in a geometry. Right? It's not this code directly, but there exist variants of this code that you can use to set down in 2 dimensions. And second, because of its simplicity, since every qubit only ever talks to 4 other qubits, when you're running your syndrome extraction circuit, there's very limited connectivity. You can imagine there are other scenarios where a stabilizer might talk to 5, 10, 20, a number of qubits that grows with system size, and that's going to be very difficult to engineer. Whereas here, since you only ever talk to, every qubit only ever talks to 4 other qubits, very simple to engineer, simple circuits. And simple circuits then means that you're limiting the spread of errors in your circuit. Okay? You can implement the circuit fairly easily. And so for many, many reasons, we really love the Torque code, and it forms the base of all sorts of generalizations. So it's no exaggeration, it's the most important thing. Also, from numerical simulations, we understand that the threshold is fairly large. There exist examples where people believe that we have already achieved physical error rates below the threshold of the torque code. So we might already be at a point where we're below this magic number below which we can scale circuits to make them arbitrarily large. And those sorts of numbers come through numerical simulations. So that's how we play off of each other. One, the asymptotic, and two, these sorts of actual concrete codes where we know how to engineer them and study them numerically. Okay. And what about the code states? Let me just say this quickly as I'm running out of time. I'm, again, going to use a cartoon. When I use this ket, I put the entire code inside a ket. And what I mean when I put this blue loop down is that the corresponding qubits on those edges are in the 1 state, and everything else is in 0. I hope that's visible for people in the back. And now, how do I represent the state where it's in the all zeros? I'm going to start with the all zero state. And then I'm going to multiply that by every possible stabilizer. So every loop that's contractible, I'm going to multiply that and create a uniform superposition. And that forms the all zero state. And how do I go from that to the 1? You'll remember that the X-type logical was the ladder operator that ran up, down. And we're going to take that and, again, multiply that by every string here. And what's nice is that when you multiply these strings, they sort of blend and merge. And really, all that matters is its topological property, whether or not the string is contractible or not. So a uniform superposition over all non-contractible strings gives you a logical state that's not 0. A superposition over all contractible strings gives you a trivial state. It's just the 0 state. So there's these deep connections between quantum error correction and geometry, which we continue to use and are extremely important in the design and understanding of quantum error correction. And this is an example of that. This is also an example of one of our favorite types of code. It's called a CSS code. And they're nice to study for many, many reasons. And one of them is this easy representation of the computational basis states, the encoded states. A CSS code is one where all of your stabilizers are only products of X-type operators or only products of Z-type operators. And when you're dealing with a CSS code, how do you construct the corresponding map that takes you from your k-qubit state to your n-qubit state? Just start with a uniform superposition over the all zeros. Sorry, start with the all zero state, and then construct the uniform superposition of multiplying by every possible Z stabilizer. And this recipe will get you to the computational 0 state. Right? So CSS codes have some nice properties. This is one of the things that I like about them, but there's lots of nice properties. Okay, so far so good?
Sorry,
yeah.
So do you want, I always feel like we mix up stabilizers. I always feel like we conflate stabilizers and stabilizer generators.
I agree.
So of course, surface code has stabilizers with Y.
Stabilizers with?
A Y in it?
Oh, that's right. Sorry, I meant to say stabilizer generators. So yeah, so I will qualify. Ken pointed out something that's important. The stabilizer generators are one particular representation for your stabilizer group with a specific choice of generators. You can pick many different generators as a basis for your code. So for example, in where is it? So in this picture here, I had a sort of a product of 2 stabilizers. And I could have used, rather than use these vertices, I could have used one vertex and this one longer loop. Or I could have used one vertex and multiplied it with a face, and that would have given me Y operators. So the stabilizer group itself is going to have all sorts of terms in it. It's just that the generators I can pick in a clean form to have only X or only Z. So thank you. Anyone else? Okay, so, oh, yeah.
Oh, could you go back to the previous slide?
Yeah.
Just wondering for a clarifying point, maybe I'm just mixing up definitions here. To make the logical 1-0 state, is it the uniform superposition over all non-contractible loops, or are we just adding the non-contractible loop?
It's the one that goes up, down. I was, sorry, yeah, being a little sloppy. It's only one that goes this way, because there's another one that goes that way.
Right.
And if you did that, then you get 1-1.
Right. So we're just adding the one up, down, the one logical
That's right.
X operator. And then essentially it looks like that operator just has an effect on the closed contractible loops where there's some, the way you've edited the diagrams when you've added the logical X operator in, it seems like there's some like a addition process happening between adding this line versus having just the contractible loop.
That's right. That's basically what's happening.
Okay.
So it's going to be like essentially binary arithmetic, because since you're only dealing with like Z-type stuff and other advantages of CSS codes, it basically is a binary process. It's only Z, and Z squared is identity, so it boils down to something that's 0, 1.
Great. Thank you.
Right. Great. Yeah, thank you. Anyone else? All right, great. As we did before for the repetition code, we can ask how we can increase the distance of your Tori code. So previously it was 3, and now by increasing the grid on which this lives, I can make it as large as I want. So if I have an L by L lattice, then I construct a code that has roughly 2L squared, approximately 2L squared physical qubits, and it has distance L. It always only ever encodes 2 logical qubits, and these 2 logical qubits correspond to the non-contractible loops of your donut. Okay, so if I did have an error, and this red string here represents a qubit that's suffered from a Z-type error, how would I see it? Again, commutation, anti-commutation, those are our only tools. We're going to use them over and over again. And these 2 stabilizers that are immediately adjacent to that error are going to anti-commute, and so they're going to raise flags. And that's all we can see. We can't actually see the state. We don't know what it is. We only see these flags, and then we need to figure out what to do from there. To make this diagram sort of simple, I'm going to dispense with these loops and just say the plus signs that represent the stabilizers themselves, those are going to be unsatisfied. They're going to say something's wrong, I'm not happy, I'm not +1. Something curious starts to happen when you work with quantum codes, in that multiple different errors can have the same syndrome. So for example, if you were to consider that string, you can show that the only stabilizers that anti-commute, the generators that anti-commute with that Z string, are going to be the ones at the very end of that string. But from our perspective, you remember, we don't see the state. We only see the syndromes. Both of these paths would have the same syndrome. So you don't know what to do. What are you going to do? And it turns out it doesn't matter. It doesn't matter because if you did one instead of the other, they only differ by a stabilizer. And so you could say, I do the correction that I think it is, and then multiply by a stabilizer to get this, what the error actually was. And that's fine, because the stabilizer leaves your state unchanged. So this idea of degeneracy is extremely useful, because it means for the price of one syndrome, you can correct multiple errors. Right? So you pack in lots of different errors into one syndrome. So it's very, very useful. And what if you had multiple pairs? Then you would have to do multiple matchings, right? So if you see this pair, would you think of the string that connects these 2 pluses, those 2 pluses, those 2? You can do any which way. And the way that you might typically do this is by saying the probability of any one edge to be affected is p. So the longer the string, the less likely it is. So I'm going to consider the combination of strings that in total has the least probability of occurring. Okay? And the way that you do this is by modifying the algorithm to the point where you can use what's Edmonds matching algorithm. It's a minimum weight perfect matching. It's this algorithm called Blossom. And that allows you to find the pairs such that in total you have the least weight. Right. And now we move on to more problems. Right, so we said the syndrome extraction, this projection operation, is happening via a circuit. And for each of my stabilizer generators, for each of these plus and 0 type, the vertex and face type operators, I have a little stabilizer generator. And in this circuit, I need to do stuff to get the eigenvalues. That's how I perform a projection. And for each of these stabilizer generators, I can design a gadget. And this gadget is going to be responsible for measuring a specific stabilizer generator. So for each generator, one gadget. I don't have time to prove that this gadget is could be used for measuring X-type stabilizers, but there exist small gadgets, and you can piece together these gadgets in a sort of modular way to measure the entire syndrome. The problem is, of course, that your circuits are noisy. We want to get some information about our state to do error correction, but that information could itself be noisy because the qubits that you're using to extract classical information are noisy. The gates that you're using to extract information are noisy. It's noise all the way down, right? Daniel Gottesman, one of the luminaries of our field, he has a quote in his book that I really like when referring to this. He's saying, who's correcting the correctors? And that really is what the problem is here. Like, everything's noisy. Right, so these are just examples of the ways things can go wrong. So your ancilla qubits can carry errors. The syndrome readout that you're looking for might be imperfect. You think you're in this space over here with this syndrome, but actually it turns out you're in the other space because some of your bits got flipped. The syndromes can be faulty, and you pick up errors. During the process of error correction, you're introducing errors into your system. And you're trying to perform a correction operation. By the way, these double lines, what they mean is that you're extracting classical information. That's what these double lines mean in this cartoon. And you're using that classical information to figure out what the error is and then perform a correction. So it's a classically controlled quantum operation. And all of this needs to happen really fast, right? That's something else that's typically not highlighted. You need extremely fast classical computation to keep up with potential speedups that you might hope to have. And if they don't happen fast enough, then you're going to have a backlog of errors, and that very quickly gets out of control. It builds up exponentially quickly, and then you're hosed. You can't recover from that. And so your decoding algorithms need to be extremely efficient, and they need to be implemented in a way that your classical computer can keep up with your quantum computer. Okay, so running out of time, so I should move a little bit faster. So other sorts of problems that you might be worried about are if your ancilla qubit that you're using to perform syndrome extraction to extract the eigenvalue of this measurement, if that itself is noisy, then so I'm going to point to that cartoon up in the top right. That's the little gadget that I'm using to infer one of my stabilizers. And I start with one error on my ancilla, and now it's spread to 2 errors on my data qubits. And then it can continue to spread as I perform the circuit, so 1 error can become 5, right? And this also is a problem, where errors can now spread and multiply over the course of your circuit. So how are we going to get around this? It's errors all the way down, but it's also error correction all the way down. So we might think to, one, encode our state. We might choose to encode the ancilla qubit that itself is used to perform these measurements, and then everything's error corrected. And this is something that Shor had proposed, using, say, cat states to perform error correction. The advantage of some of these more general proposals is they work for a wide range of codes. The disadvantage is that once you start to encode your ancilla, now you're increasing the number of qubits that you need for running a fault-tolerant circuit. Not only do you need an error-correcting code to protect your data qubits, you need an error-correcting code to protect your syndrome qubits. You need an error-correcting code for every little thing. It can get out of hand pretty quickly. For particular codes, however, again, this is one of the reasons that we like the Tori code. It's possible to get away with doing this raw circuit where the ancillas that are used to perform your measurement are not encoded. And because every qubit only talks to 4 other qubits, things can go wrong in very limited ways. There's only a few possible things that can happen. So it's not that you can get an arbitrarily bad error. You can have a very simple type of, or maybe even predictable type of error propagation. But it still could be that the measurement, the qubit that you have was incorrect, so you don't have the correct syndrome. And so you have a sort of an indirect error correction process. And the way that you do this is by repeating the syndrome measurement process d times, and using this aggregate information over d measurements to then tell you what the correction operation ought to be. Okay? So there's still some error correction going on. It's just that it's happening without introducing too many other ancilla qubits. Okay? There's still some error correction that's happening for your syndrome. You're doing them many times over to ensure that at least one of them, or like a majority of them, are right.
You
You said we need to repeat it d times. Is there like any logic why we need to do d times or like less or more?
Yeah, so remember we talked about the repetition code? What you're doing is forming a repetition code in time. So your repetition code, previously we thought about it as a code in space, but this now becomes a code in time. So your error correcting code, the entire syndrome extraction circuit, is now going to be able to resist errors that are happening across one time slice, but also across multiple time slices. So it's like the entire object across space and time is now robust. It's a repetition code in multiple dimensions.
Thank you.
Anyone else? Yeah.
I think I just missed at the end. So you said that you still need a single ancilla, but you're just repeating it.
That's right. And that way, you're not using any extra qubits. You're still using that one physical qubit for performing your syndrome measurement over and over again, but
You're paying in time.
you're paying in time. That's right. Yeah. So I know that some things were not explained in detail. For example, I haven't really told you why this gadget does what it's meant to. There isn't time for that. This is just meant to be like higher level overview of the sorts of things that we need to deal with in error correction and how to actually piece things together in modular ways and some solutions that we have to these problems. But if we want to talk about things in more detail, I'm happy to. I think it's the end of the hour, so I'm not sure if there's like a break or something at this point.
Yes, there is a break. So you guys have a quick 30-minute break, and the next session, he'll be back. So if you have questions, you can think on it, come back and ask. The next session will start at 2 p.m., okay?
Yes.